Three is just cool. Everything you get three-dimensional, multivariable calculus. Well, we start in 12.1. Well, that's where we start this course. It's an introduction to the three-dimensional coordinate system. All right. So, three-dimensional coordinate system. That's where we start. All right. Now, but we'll still do things, everyone, in the XY plane. We'll still be working math problems in two-dimensional space. You can call that three-dimensional space. Have you ever seen that? Sometimes people call that for all reals. Sometimes people refer to this as like two space. You can think of that as three space if you want. But that's what we're talking about. We're going to begin introduction to three-dimensional coordinate system. I put a PowerPoint. I'm not a big PowerPoint person, but I did put one in Canvas. If you're not again in Canvas, I'll let you know at the end of class on just this introductory to the three-dimensional coordinate system. I titled it Pythagorean Theorem because you can notice a lot of things we do in this one section are based off the Pythagorean Theorem. That's why I titled it that. I was like, that's where it came from. So I'll start with that. I mean, it's just the idea of I'll be in two-dimensional space and then we'll jump. A lot of you are aware of this, but let's just start here. I've got a couple points here. Let's say I got to get the distance between these 2 points. x1, y1, and x2, y2. Right? This is derived from, I want to get the distance between these points from the Pythagorean theorem, right? A squared plus b squared equals what?
C squared.
C squared, come on in. And so, I can make a right triangle that, right? So I'm just going to derive this, it only takes a second. But I gave a long formula sheet out. And so a lot of these formulas, you go, man, I have a hard time remembering these and memorize them. If you know where it's derived from, it's pretty easy. You can always back up to this, and it kind of stays in your memory. So I thought we'd do that. I'm going to figure out what's the distance from this point to this point. And so what I can do is, well, what's the distance here? I can erase these 2 points now, just so we can focus on this. This right here is x1. This right here is x2. So isn't the distance between here and here x of 2 minus x of 1? Okay. And how about these 2 points? What's the distance between those 2 points? If I put absolute value around that, everyone, that represents the distance between those 2 points. And it'll always be positive, no matter which way I subtract. Well, this is a y sub 2, and that's some y sub 1 value. So this would be
y2 minus y1.
y sub 2 minus y sub 1. I'll put those bars around it to represent the distance. And I'm looking for this, and we're saying I can get the distance formula if I do Pythagorean theorem. That squared plus that squared equals this squared. We can call it distance here, d for distance. And we get it. We're like, what is it? All right. D squared, a squared plus b squared equals c squared. And thanks for bearing with me. I won't derive everything today, but I thought the first problem would be neat for us to derive this. And you go, why? Because it helps with our memory. We got to retain these formulas. We know where formulas come from. We can always do it again. But I need a formula for d. What do I do to both sides?
Square root.
And that's why when this is a funny looking formula. The distance between 2 points in two-dimensional space. Oh, and you know what I'll do before this? I apologize. If those straight bars that represent distance is upsetting you, well, I can now put parentheses. Because isn't a positive or a negative squared always positive? So we can make these soft parentheses. All right, let's do that. And now, if I need d, it's an ugly looking formula. But it's not that bad. I just take the square root of this right side.
Can you not do it like change in x then? Like x2 minus x1?
You can. I like that. I'm going to write it that way. The simpler you can write it, the simpler you can remember this. So you're telling me, Art, I like that you said, why don't you just call that change in x? Anybody use that symbol for change? For difference? Okay, leave this wall on the right. Pull this wall away. You sure?
Yeah.
I gotta make sure this thing doesn't get in the way. Yeah, distance between x's. squared, and then add the what? That's not a bad idea, just an easy way to remember it, right? So there you go, and that's the distance between 2 points in space. Very important, but it came from which theorem? Pythagorean theorem. Well, now we're going into the three-dimensional coordinate system. Then in a three-dimensional coordinate system, I mean, we can throw the z-axis this way, the y-axis this way, and an x-axis this way, and we're talking about plot points that have an x and a y and a z coordinate, right? Yeah. 1 point, x, y, z. Was everyone okay with that? So we derived it. By the way, that's what's in that PowerPoint. You know, it's not too long, but it gives you an idea. How's all this stuff derived? And you'll just notice, oh man, everything comes from the Pythagorean.
You just need to see everything branches from it.
Exactly. Everything branches from it. So I'm not going to derive it for 3 space. It's in that PowerPoint, but I bet you can extend it now. What do you think if 2 points, when we're in 3-dimensional space, you have an x, y, z coordinate? What do you think the distance from it would be? Just extend the thing.
So change in z,
Okay, Phil, just extend this longer and put a plus and then a what?
change in
Z
z.
sub 2 minus z1 squared. Exactly. That's why we have to go here and derive it right now. If you want it, it's in the book or it's in my PowerPoint. So I'm going to put that up here. That's like a very important formula for our class. We use this often. We'll get into vectors today, everyone. If you've never had vectors before, super. If not, it's not a big deal. Teach you everything about it, but we got to find the length of these vectors, and that's how we do it when it's 3-dimensional space. That's exactly what we do. And you can think of it this way too. But that's easier. You might go, well, I'll just put a plus change z squared. So there we go. That's the distance between 2 points in 3-dimensional space, right? Awesome. Might as well add 2 more because it's going to be so quick, everyone. I mean, it's just, like he said, everything branches off this Pythagorean theorem. How about a circle? Watch how fast we can do this. Now, when I have a circle, I don't know, this over here, right? 2-dimensional space? There's the circle. Let's call the center h comma k. And that's the center of my circle. And let's put a point on the edge, x comma y. Well, what would be the distance of that radius? So when the radius is the distance from the center out, right? Oh, Jesus, Joe. What would be that distance of that? They're all called r for radius in a circle. What would be the distance between those 2 points?
X minus h squared
So x minus the h squared
plus y minus k squared.
plus y minus the k squared. Okay, I'll write that out. Is that not what's true for that circle? Hey, can I erase that figure? Here comes, and in a circle, there's the radius. We're saying, well, then the square root of x minus the h squared must plus the y minus the k squared. Okay. But d is represented by what letter? R. Now I'm color code. Now you're the radius. And then when you square both sides, you just got the equation of a circle. Isn't that cool? Square both sides, what do you get?
X minus h squared plus y minus k squared.
Outstanding, there it is. And that is the equation of a circle. Although a lot of times it's going to be way easier in this class. In 2-dimensional space, most of the time it's centered at the origin. Most of the time it's centered at the origin. So what happens to the HK? Yeah, so when you're just going to have, you're going to notice in this class, we just got a little circle right there, and you're like, the radius is 2. And so you're like, oh, okay, x squared plus y squared equals 2 squared, which is 4. Because the HK is just going to be what? 0. You know? I mean, sometimes it gets shifted and all that. But most of the time, it's centered at the origin. Cool. So, what about a sphere? I'm going to go in here, I'm trying to make like a basketball, like a sphere. Well, then that should be very similar. Because everyone, here's the center. Except I called that the center h comma k. Maybe I could say this center is, you know, and maybe I shouldn't put it right at the origin. Let's put it somewhere else. Let's just put it somewhere in space. make it look like a sphere, everyone. So it's three-dimensional. There's the center of the sphere. All right, here's a point X, Y, Z on the edge of the sphere, and there's the center H, K, L. And there's the radius of the sphere. So let's invent, okay, aka derive, the formula. Let's do it for the formula for the equation of a sphere. Well, we won't use this one, but we'll use what? That one right there. Do y'all agree? Let's invent right now. What would be the equation of a sphere? That's the set of all points at distance r. We can call that r for radius from the center HKL. Anywhere in three-dimensional space. That's a sphere. It's a set of all points anywhere, you know, from that center HKL. Well, what do we get here?
X minus h squared plus y minus k squared and z minus l squared.
And then I'll square both sides. And this is going to look just like the circle, isn't it? Except it's going to have this little piece at the end. X minus h squared plus y minus the k squared, and then the z minus the l squared. R squared equals what? There it is. I'll get out of the way so you can see this. But this is just, we're having fun here. It's like, oh my gosh. All this is coming from Pythagorean theorem. That's the equation of a sphere. That's the equation of a sphere. You know, welcome to three-dimensional space. But a lot of times, you're going to notice in this course, that sphere is centered at the origin. So what will it look like? The h and the k and the l will just be what? 0, 0, 0, and you're going to get an equation like this. That's a sloppy looking z. Just an example. There's a sphere, it's centered at the origin. What's the radius though? It isn't 4. 2. The radius is 2. And that's a sphere, just centered at the origin. A lot of things like that. Cool. So I thought, you know, just that's the introduction to the three-dimensional coordinate system. We'll do some problems from 12.1. I'll give you some examples. You'll find some of these on that problem set. All right, some problems where you know, it deals with this. So hey, man, that was a lot of formulas, but you know, I don't want to. Let's get to some real problems. It's probably getting tired of me deriving things, but it's neat. If you know where something comes from, thanks for bearing with me on that. Boy, you can do so much with this. And that's why I wanted to make sure you understood how all that stuff was derived. So, this is the equation for a sphere, right? That's just the distance between 2 points in space. So I can get this out of the way. All right, let's go back to a sketch of that three-dimensional coordinate system. Let's do this problem. Now let's find the distance. From the point two, 3, 4. To the YZ plane. Now we should get a sense of this. You don't have to draw a perfect picture, but I'm going to draw that again. All right, Z-axis, I'll just always point that straight up. The Y-axis, you can chuck that off to the right side somewhere. You could slant it if you want. And then the X-axis, just have it go this way somewhere. So we get that sense of three-dimensional space. You know, it's not quadrants anymore, now they're octants. Right? But sometimes it's weird because I'm drawing on a two-dimensional board here, trying to describe something three-dimensional, right? I understand it. Sometimes it might take a little while to get used to that. Feel free to come back to like this classroom and think like, okay, this is like one of the octants here, sitting in here. And then below this is another octant. Maybe on the other side of that wall is another octant.
The table.
You know, you sure can.
Yeah, the X,
I think that's great. You can, Art, that's great. You can even take like that wall and go, there's my Z-axis. You use things like that even, I know I'm using this room right here, but you can use something like in your own like home to better see this. Go, I'm gonna put that in the corner of the wall. Mom, you don't mind me drawing on the board wall, do you? And all that stuff. Well, here it is. We gotta find the distance from this point to this point. Well, all I need is the distance formula, right? But this idea of YZ plane, that's this plane. So in the YZ plane, all the points in the YZ plane, one of those three variables is taken on 0. You know what it is? In the YZ plane, oh, I heard it. What letter? X equals 0. Would you put that down? In the YZ plane, any point in that YZ plane, the X coordinate will be 0. I mean, I'll give you an example. Here's a point in the YZ plane, 0, 100, 200. It's sitting in the YZ plane. But the X value is what? 0. And I bet you can extend that. What do you think happens like in the XY plane?
Z0.
Z is always 0.
That's what we're used to dealing with.
Yeah, because that's what we've always dealt with for years. Algebra 1, college algebra. I'm thinking of all the classes I teach. Pre-calculus. Z was 0, Z was 0, Z was 0.
So
And then one more, I guess, what's the other plane? The XZ plane,
y is 0.
Y is 0, right? So when I gotta find the distance from this point to the YZ
I
plane.
got one question though. So
Oh,
like
sure.
in the YZ plane, since x is 0, then is z the dependent variable?
So what we'll do is, you and I are gonna pick a point, because when they say the distance, they want you to take the shortest distance.
Uh-huh.
So I'm gonna specify that, everyone, and be clear about when the author writes this, and you see that, that problem being asked for you to work, they mean like the shortest distance. So you don't think like, wow, I could go all over the place. They want you to take the closest route. So what we're gonna do is, the next point we pick we're definitely gonna let x equal what?
0.
0. So initially you and I think, and we're like, well, you're gonna be 0. But you know what we gotta use for this? Because we want the shortest distance, we're gonna use those same numbers. It's a what?
3 and 4.
3 and a 4.
Ah.
And if you want to get a sense of this, we can plot it. We can go in here and like get it. What are you doing? We're going straight to that point. We're just taking the shortest distance there. And we take this and we put it into the what? Yeah, right there in the distance form. And we'll do it now. But if you wanted to plot this, you're like, here's x0. I go 3 notches.